Let's look at Boyle's law. So Boyle observed that pressure times the volume equal constant. So let's just do a little experiment. This is what he observed. So let's say our pressure is 1, our volume is 20, so that means our constant is 20. Let's cut the volume in half. Boyle said that that should equal 20 still. And so what does the pressure have to be so that I get that 20? And the answer is 2. So we see that if we half the volume, we double the pressure. Let's do this one more time. So let's half the volume. And again, Boyle said it should equal 20. So what does the pressure have to be? And the answer is 4 atmospheres. So this is Boyle's law. Now I said before that all of the gas laws are derived from Pivnert, or the ideal gas law. So PV equals nRT. If we have the same sample of gas, so our moles is the same, and if we have our gas law constant is going to be the same, and if our temperature is the same, then I can take this Pivnert and I can get rid of this side, and this is Boyle's law, PV, and then you're going to change something and see what happens to the pressure. So that's what we were doing here. We were changing it. So this is his formula. P1 times V1 equals P2 times V2, meaning I can take the pressure and the volume of the first situation and I can change either the pressure or the volume and I can calculate the new pressure or the volume. So this is Boyle's law, pressure and volume. By the way, you don't have to know the scientist's name. I will never ask you that and the AP board won't either. You just need to know how to do these calculations. So this is that logic of getting Boyle's law right here. Because they have the same constant, then we can put them equal to each other. And then in class, we can look at changing the pressure. So if my pressure goes down, what happens? And we can also look at the Cartesian diver, which in this case, we make the pressure go up. And I will try to link some YouTube videos at the end of this so you can see those. Here's another picture of Boyle's law. So here we have a certain volume and a certain pressure. And then if I cut the volume in half, so if the volume gets cut in half, I see that my pressure, it doubles. So this is an inverse relationship. So if one goes up, the other one goes down. Here's some graph representations of this showing that if your pressure goes up, your volume goes down, or if your volume goes up, your pressure goes down. Let's look at an example where we can use Boyle's law. And I'm going to know what formula I am going to use by identifying what all the numbers and their units are in my written problem. So this says if a scuba tank has a capacity of 10 liters, so I know that's a volume, is filled with air to 500 kPa, that's a pressure unit. What will be the volume of air? So my second volume, I don't know what it is. I'm going to solve for that. And then here is a second pressure. So again, I had my V1 and my P1 because they're the first ones I read. Those two go together. And then I'm going to find the second volume and I'm given a second pressure. So write your formula. P1 V1 equals P2 V2. And again, it all comes from Pivnert. Because moles are the same, R is the same, and temperature is the same, I only have this portion, and I just put it equal to itself. I am solving for the second volume, so I'm going to divide each side by the second pressure. So this cancels, and I'm going to get V2 is equal to P1 times V1 over P2, and I can plug in my numbers. And I already identified where they are, and you can see that my pressure units cancel out, and I'm going to be solving for liters, and when I do my math, I get 7.12, 3 sig figs because my liters has 3 sig figs. So there is my liters for Boyle's law. So again, I know how to use Boyle's law because I identified in the written out problem what all the numbers are. So then I only saw pressure and volume units. So then I only use pressure and volume in my formula. Let's go ahead and go on to our next gas law. But before this, I want to tell a story from my own life. When I was 16 years old, I worked at a florist, And I just did odd jobs around the shop. I delivered flowers. I rang people up at the cash register. And this one day, my boss wanted me to drive to the local Hallmark store and to get a dozen helium balloons. So it was a very hot day, and I took my boss's little hatchback car, and it was stick, and I was so excited because I had just learned how to drive stick. And so I drove all the way to the Hallmark store, and I walked in to the store, and it was one of those times where you walk from a very, very hot afternoon into almost a refrigerator atmosphere in that Hallmark store. I went to the teenager behind the counter and said, I would like a dozen helium balloons of various colors. And she replied to me that she didn't know how to use the helium tank. And being the confident teenager that I was, I said, well, if you'll let me use the tank, I know how to use it and I can blow up the balloons. So I went and I proceeded to blow up a dozen balloons and tied them with all the strings. And then I took my dozen balloons after I paid for them and walked out of the store into trying to get a dozen balloons into that small little car. So I opened up the back and I started stuffing the balloons into the car, and all of a sudden, to my horror, I heard pop, 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 pop. All but two of the balloons popped. Humiliated, I went back into the store and told the teenager I needed 10 more balloons, which I paid for. And this time, I did not fill the balloons so full of helium. Because what happened to the balloons when I left the cold, refrigerated store to go to a very hot summer's day? What happened was Charles' law. In Charles' law, we are looking at volume and temperature. So in a balloon, the pressure stays the same. And also the amount of gas that's in the balloon stays the same. But my volume and my temperature can change. And what I learned firsthand is that when the temperature goes up, the volume also goes up. And so because I had overfilled those balloons, they expanded so much that they popped. So let's look at Charles' law. So again, I'm going to go back to the ideal gas law. In this case, my pressure stays the same, so I'm just going to cancel it out. The amount of gas I have in there stays the same, so that's my amount of my moles. Gas constant will be the same, and so I am just left with these two variables, V and T. So if I divide each side by T, I get V over T, and if I put it equal to itself, and then do situation 1 and situation 2, then I have Charles' law. You could also reverse it and have the temperatures on top and the volumes on the bottom. That would give you the same answer also. And so the relationship of this is as temperature goes up, volume goes up. As temperature goes down, volume goes down. This is a direct relationship. Now, a note for this, temperature must be in Kelvin. If you have a negative degree Celsius, when you do this calculation, you'll end up with a negative volume, which is not possible. Okay. Using Charles' law, this is how they were able to determine what the absolute temperature is when all motion ceases or when we're at zero volume. And we do this by decreasing the volume and decreasing the volume by lowering the temperature. And then at a certain point, we take all our data points and we extrapolate the line, or in other words, extend the slope. And we're able to figure out that 0 Kelvin is negative 273 degrees Celsius. Another application of Charles' law is ping pong balls. If you've ever seen a dented ping pong ball, you can't play with it anymore. Well, don't throw them away. Use Charles' law to get your ping pong balls back. So just take the ping pong balls and put them in warm water. Even boiling water will do it faster, because as you increase the temperature of the gas inside the ping pong ball, that will increase the volume, and you can get perfect ping pong balls back. Let's do a problem with Charles' law. When I read a problem like this, I don't know off the bat that I'm going to have to use Charles' law, but I'm going to identify what's what in the equation. So the first one, 223 Kelvin, that's a temperature. And I'm going to call it my T1 because it's the first temperature that I read. And then this one, this is my volume. I'm going to call it my V1. And it says what volume, so that's going to be my second temperature, and I'm going to solve for that. And then it says the pressure is kept constant and the temperature is increased. So there's my T2. So write Charles' law, V1 over T1 equals V2 over T2. And I'm going to solve for V2. So I'm going to multiply each side by T2. And that will cancel out. I'll get V2 equals V1 over T1 times T2 on the top. And then I can just solve this. So V1 is 100 liters. T2 is 350 Kelvin, and I am in Kelvin. And at the bottom, temperature 223 Kelvin. So Kelvin's going to cancel. I'm going to be left with liters. And my answer is 157 liters. So again, Charles' law, where the pressure is kept constant and also the number of moles. Let's look at our next gas law. This is Gay-Lussac's law. And he looked at pressure and temperature as changing. So again, if we looked at PivNert, in this case, the number of moles is staying the same. Of course, my gas law constant is going to be the same. And this is where I have the same volume. So I'm looking at some sort of container that won't expand. And so I can increase the temperature and see how it influences the pressure. And so this says, what is the constant? So volume is the same. So again, I should have some sort of container, maybe some glassware that it just is stoppered. And then I can heat it up and see what happens to the pressure. Please don't go and heat anything that is sealed because the container can explode. So this would be more of a controlled experiment where I know that I'm going to be safe if I heat something that's a closed container. And just as a reminder, make sure that you're in Kelvin for your temperature. This is the theory behind pressure cookers. So in pressure cookers, I have a lid that fits on very tightly, and it's a very thick pan. If you look at a pressure cooker pan, it tends to be a little bit thicker metal, so not a really flimsy material, so it can withstand the pressure. The reason that foods cook quicker in a pressure cooker is because you can increase the temperature, and so then that cooks your food faster because it's the heat that cooks your food, not the temperature. So on, again, how a pressure cooker works, it's a closed volume. So again, the volume is the same. And I'm going to have the same amount of stuff in there when I put that lid on. And as I increase the temperature, that will increase the pressure. And I'm able to get higher temperatures than I normally could. Let's go ahead and do a problem with this gas law. And again, I'll know to use this gas law once I read through and identify what everything is in the problem. So this one right here, this is a pressure unit. I'm going to call it my P1. This is my temperature unit, and I know I automatically need to convert it to Kelvin. This is going to be my T2, and that one's going to be 298. I just solved for the new pressure. So this one I'm using kind of a non-standard pressure, but this law works just as good. So P1 over T1, if you did reverse it, you would get the same answer. In other words, if you had the temperatures on the top. And it says I'm going to solve for the P2, so I'm going to multiply each side by T2. So I get P2 equals P1 T2 over T1. And if you don't want to manipulate your equation, just follow your algebra rules and you should get the same answer. My K's cancel, and getting my math, I have 2034 psi. We didn't change the temperature too much. If I were to do sig figs, there's 3 sig figs, so that would be 2030 psi. Gay-Lussac also discovered that there's a proportional volume. So he looked at combining hydrogen and oxygen to making water, and this is might be a sample experiment. So 100 milliliters and 50 milliliters, and he found he got 100 milliliters. And then if he cut this in half, he got the same ratio. So the same ratio by volume. And he couldn't understand the ratios, why this was so. Then along came Avogadro. So Avogadro's law, or the law of combining volumes, if we look at PV equals nRT, and if we have the same temperature and the same pressure, and of course our gas law constant is always the same, I'm left with just volume and the number of moles. And so you can look at this problem with the moles on top or the volume on the top, but you get the same thing. And so what Avogadro discovered is it's not the mass that's reacting or the volume that's reacting, it's the number of moles reacting. And remember, Avogadro was the one that gave us Avogadro's number, or at least it's attributed to him and named after him. So Avogadro, working with gases, he said that 1 mole of any gas occupies a volume of 22.4 liters at standard temperature conditions. So looking at Avogadro's law, we found that the number of moles and the volume changes. So that means that pressure and temperature stay the same. And we also know that the volume ratio of any two gases in a reaction at a constant temperature and pressure is the same as a reacting mole ratio. So that volume and that mole, there is a relationship there. So let's do this problem. A catalytic converter in an exhaust system of car uses oxygen to convert carbon monoxide to carbon dioxide. If the temperature and pressure are constant, what volume of oxygen is required to react with 125 liters of carbon monoxide? So we're first going to write a balanced equation, and on the AP test this would be given to you, but we do have oxygen reacting with carbon monoxide and making carbon dioxide. And to balance this, I need to put a 2 in front here and a 2 in front there. That will balance out the oxygens. And then let's go ahead and write our formula here. So I'm going to do the moles on top and the volume on the bottom. And from the balanced equation, that's where I'm going to get my mole numbers. So rearranging this, we want to solve for our oxygen. And we have our moles of our oxygen is 1. Volume of our CO is 125, and divide that by 2 moles. And when I do that, I get my answer 62.5 liters. So that's using a balanced chemical reaction and Avogadro's law, and looking at the mole ratios and the volume that has been given to us to solve for the other one. Let's do one more problem. What volume of hydrogen gas forms when 150 milliliters of ammonia, so this is the volume of my ammonia, when it decomposes, and then here's a balanced equation they gave for us, and it says what volume of nitrogen forms. So we want to find the volume of hydrogen, and you want to find the volume of nitrogen. So let's write our formula. So we know about ammonia, the NH3. We know both of those. So moles of NH3 divided by the volume of NH3. And let's do the hydrogen first. So moles of hydrogen divided by the volume of the hydrogen. And we are going to solve for the volume of hydrogen. The moles of the hydrogen times the volume of the ammonia divided by the moles of the ammonia. And we get 3 moles times 150 milliliters divided by 2 moles. And our final answer is 225 milliliters. Okay, so that's the first part. Now let's find the volume of the nitrogen. So this time we again are going to have our ammonia that we know here. And we're going to look at the nitrogen now. Let's plug our numbers in. And my final answer I get is 75 milliliters. Let's look at the combined gas law. If you look at the ideal gas law and you look at a situation 1 and a situation 2 and the mole stays the same, I can get rid of N, and of course R would be the same. And if you divided both sides by T, you would get PV over T and then put it to itself. And you do 1s and 2s. This is what's called the combined gas law. This is used when pressure and temperature and volume are all changing. And then please remember, for the temperature, you always need to be in Kelvin. So let's do an example with this combined gas law. These tend to be quite lengthy. So go through and identify what is temperature, what is pressure, what is volume. So this first one, this is volume, my first volume. This is pressure, my first pressure. My temperature, 25 degrees Celsius, that's 298 Kelvin, and that is my first temperature. All right, and it says, what is the volume? So that's my V2 I need to solve for. And there is my second pressure, and there is my second temperature. And again, change it to Kelvin, so this one would be 288 Kelvin. All right, so now that everything's identified, let's write the combined gas law. We are solving for V2, so I'm going to multiply by T2 over P2. So I get V2 equals P1 V1 T2 over T1 P2. And let's plug in all the values. Notice that in my volume, you do not have to be in liters for these, but you're going to write your units anyway. And so you'll see that in this case, the units is going to be milliliters for the answer because that is my V1 unit. Cancel out your units. So atmospheres cancels, Kelvin cancels, and you are left with 725 milliliters. Looking at sig figs, it looks like I only have 2 sig figs, so I would say 730 if I was doing sig figs.